Thermodynamics and statistical mechanics describe the behavior of systems with many interacting degrees of freedom. Systems have a huge number of microscopic states, or what we call microstates, available to them, and they'll continually pass between these states. The only reason we have hope of saying anything sensible about this is that these states obey nature's symmetries and conservation laws. So one of the things that we want to learn how to do is to actually count states. And we're going to use two types of counting in this lecture. We're going to count microstates. So let's introduce a couple of basic principles and then move on to a couple of sort of interesting examples. So if we're going to count microstates, the first thing we have to do is introduce two principles. One is the addition principle. If two operations are mutually exclusive, and the first can be done in m ways, while the second can be done in n ways, then one or the other can be done in n plus m ways. What we call sort of or probabilities would add in a sense. On the other hand, there's the multiplication principle. If an operation can be performed in n ways, and after it's performed in any of these ways, a second operation is performed in m ways, then the two operations can be performed in n times m ways. Let's see how this might apply. Call this the flags on a ship problem. I have a ship with a flagpole, and I can hang any of 4 distinct flags on the ship: X, Y, Z, and W. And by hanging a subset or some set of these flags, I can send a message, essentially a code, to other ships or other entities. So the question I would ask is, how many signals can it send, assuming at least one flag must be on the flagpole to create a signal? Okay, so that's the problem. Make it a little bit more interesting. There are two ways to do this. One way we say that the order of the flags matters. It can't just be that I put up an X and a Z, but I have to put it up as an X and a Z, not a Z and an X. The other way is to say the order of the flags doesn't matter. So if I put up 2 flags and they're a W and a Y, whether I put the W on the bottom or the W on top, it sends the same message. So you see these 2 different types of possibilities. Let's start with rule 1. Okay? Let's say that the order of the flags actually matters. Go through it step by step. Suppose I can only put 1 flag up there. If I can only put 1 flag, then I get 4 signals, right? Which is to say I have 4 factorial over 4 minus 1 factorial possibilities, or just 4. If I have 2 flags, now I have 4 factorial over 4 minus 2 factorial possibilities, or I could send a total of 12 signals. With 3 flags, that would be 4 factorial over 4 minus 3, factorial, or 24 signals. And again, the order matters. So whether I put suppose I have 3 flags, X, Y, Z. X, Y, Z is different than Y, Z, X or Y, X, Z. If I have all 4 flags, that's 4 factorial over 0 factorial, which is just 4 factorial, or 24 signals. So that's how many messages I can send if the order of the flags actually matters. On the other hand, suppose it doesn't matter. Now, for one flag, I can send 4 signals over 4 minus 3 factorial times 1 factorial, or 4 signals, just like before. If I have 2 flags, I have 4 factorial over 4 minus 2 factorial times 2 factorial, or 6 signals. With 3 flags, I have 4 factorial over 4 minus 3 factorial times 3 factorial, or 4 signals. And if I have 4 flags, of course, I can only send 1 signal. So, it very much matters, in this case, how I order the flags, and in this case, it doesn't matter how I order the flags. And you see that the possibilities are completely different. Under the first rule, we call this the number of permutations of the system. That's when the order matters. In the second rule, we call this the number of combinations. So there's a difference between permutation and combination in the world of statistics, probability. When we say permutation, we're talking about an arrangement of set of n distinct objects in a definite order. The number of distinct permutations, of course, is n factorial. So think of it this way. Suppose I have n objects and I have n bins to put them in. And I can only put 1 in each bin. Well, there are n choices for the first bin, n minus 1 for the second bin, n minus 2 for the third bin, all the way down to when I get to the nth bin, I only have 1 choice for the nth bin. So I can fill all n bins in n factorial ways. n minus 1, n minus 2, n minus 3, and so on and so forth. So this is the number of permutations. Now, if I want to look at the number of different permutations of n objects taken r at a time, that's going to be equal to n factorial divided by n minus r. So in the case of the flags where the order mattered, if I looked at 4 permutations taken 2 at a time, 2 flags, 4 permutations taken 3 at a time, 3 flags, you see that the number of possibilities or permutations increases. On the other hand, if we talk about combinations, now we're saying I have a selection of objects without regard to order, and I can write the different number of combinations r at a time, n factorial divided by n minus r factorial times r factorial. So you see the difference between permutations and combinations. It's this other factor of r factorial in the denominator. It looks a lot like the in fact, this looks like the coefficient in the binomial distribution. So what I can say is R distinct objects have R factorial permutations, and if I say CR to the n is the number of combinations of n distinct objects taken R at a time, then R factorial times CR to the n will give me the number of permutations. And so, or if I turn it around, CR to the n is equal to n factorial over n minus R factorial times R factorial. Combinations, permutations. Do one other example along these lines. It's called the bus example. I have the following situation. I have a bus that has 7 forward-facing seats, and I have 6 rear-facing seats, like so. Suppose I have 9 students aboard the bus, 3 refuse to face backwards. Okay? 9 students. So I have a total of 13 seats, 9 students, but 3 of those students don't want to ride backwards, or face backwards when they ride. So I ask myself, how many different ways can the students be distributed in these seats on the bus? Now, to do this by hand would take quite a long time. But we can do this in about 3 steps. So first, I know that 3 students have to sit in the 7 front-facing seats. So, to do that distribution, I'll do a 7 choose 3. So, the probability for the possibilities, permutations for those 3 students, P7, 3, I can write as 7 factorial over 3 factorial, which is 210 possible ways I can do that. I'm sorry, 7 factorial over 4 factorial, 7 minus 3. For the remaining students, so these are the 3 that have a preference. For the remaining students, we have a total of 10 seats, and it's 10 seats, choose 6. So I have 10 factorial divided by 10 minus 6 factorial, or 10 factorial over 4 factorial, which gives me 151,200 possibilities. Now, to find out the total number of configurations, or number of distributions I can get, all I have to do is multiply these 2 numbers together, and so the total is 31,752,000. Those are the total number of possibilities of arranging those 9 students where 3 of them refuse to sit in the rear-facing seats. Pretty amazing. One more kind of quick example. Let's go to something more physics-oriented. Let's do spins. We talked about spin up and spin down, or positive and negative spin. Suppose I have the following situation. Suppose I have a possibility of being in 2 possible states. So I've got spin up or spin down. And so the total number of microstates then, if I have n spins, is just 2 to the n. They can either spin up or spin down. So if I have 10 spins, for example, the total number of possibilities, I'll use omega to indicate the number of possibilities, is going to be 2 to the 10, or 1024 possible ways of configuring 10 spins. That can either be spin up or spin down. If I have 1,000 spins, that's equal to 2 to the 1,000. That's going to give me something like 1.07 something something times 10 to the 301st power. And you can imagine 1,000. Suppose I were to take a small magnetic crystal with 10 to the 23rd atoms. Forget it. You can't possibly get that number. It's gigantic. And one of the things that we want to illustrate with what we're doing here is that when we use numbers that are seemingly kind of large, like 1024, the possibilities become enormous. And then when we talk about numbers on the order of, let's say, Avogadro's number, and we talk about those possibilities, those become extremely unlikely to count. We will find ways, though, of making this more manageable as we go deeper into the course. Let's go back to the two-state paramagnet. Let's follow on with a system similar to this. Let's define N as the total number of spin-down particles plus the total number of spin-up particles. The system has one macro state for each value of N up. It has one macro state for each value of N down. And so what we define is a multiplicity for the system, omega. Multiplicity is an indication of how many possible states you can have with a given configuration. So the number of possible states I can have, let's say with spin up, I can write as n factorial over n up factorial times n down factorial, as in the case of what we did with flipping coins. So let's say that the spin up particles point in the same direction as a magnetic field, so my n ups point that way, and the spin down particles point in a direction opposite to the magnetic field. We can associate an energy with this, and the energy is equal to the number of up spins minus the number of down spins times the magnetic moment times the magnetic field. I should say mu dot B. A second example of this is what we call the Einstein model of a solid. Now we're going to study about the Einstein model much later in the course when we look at specific heats and solids. But for now we're going to use the sort of the bare bones approach Einstein took to take advantage of how to do a multiplicity calculation in statistical mechanics. So just to sort of give a brief introduction to what this does. Solids appear solid as non-moving entities, but they're really not. It's an illusion. All of the atoms of the solid are constantly in motion. We can't really detect that. What we often do, though, is when I picture a solid, I think of a large number of little spheres, maybe connected by springs, harmonic oscillators, if you will. Einstein used this idea to try to model a solid and from that calculate the specific heats of solids. Now, we're not going to go that far right yet, but towards the end of the course we will. It's a very simple model. It's not a correct model by any means, although it certainly has some qualitative value to it. But this is what he did. Let's suppose that we have a three-dimensional solid. Let's suppose that it's composed of these oscillators, and they can oscillate in all three dimensions. And let's say that its energy, the energy of the oscillators, is quantified as the product of Planck's constant h times the frequency of oscillation of these oscillators. One of the things that Einstein was able to point out is that the energy of these oscillators at the 0 point is not 0, but is actually 1/2 h times f. Again, this is something we will do down the road, or you maybe will do in the quantum mechanics course when you solve the harmonic oscillator problem, or you solve the Schrödinger equation for the harmonic oscillator. Oftentimes we will write this energy, though, instead of h, we'll write it as 1/2 h bar omega, where h bar is Planck's constant divided by 2 pi, and omega is 2 pi times the natural frequency. What Einstein found is that if I have n oscillators, so that is to say I have n over 3 atoms oscillating in 3 dimensions. Each dimension is its own oscillator. The general formula for n oscillators, and let's say each oscillator has a unit of energy, Q. The general formula for finding the possibilities, the number of oscillators with energy Q, I can write as Q plus n minus 1 taken Q ways, or Q plus n minus 1 divided by Q factorial divided by n minus 1 factorial. So I can calculate the multiplicity, the number of ways I can configure a system with 30 oscillators with 30 units of energy. So all I have to do is put 30 in for Q, 30 in for N, and I'll calculate a multiplicity that looks like, well, this would be 59 factorial divided by 30 factorial times 29 factorial, or 5.91 times 10 to the 16 possibilities. So this is a good example. As I say, we will go into much deeper detail about the Einstein model when we study solids, but this is a good example of how to calculate a multiplicity. If I have this many oscillators and I am distributing energy in any number of ways, I can calculate the number of configurations I would have, and you see that the number is enormous. And one of the things that we want to drive home in this particular section of the course is we want to show that the numbers can be very, very large. And the larger the numbers are, the more confident you can be in the results that you predict. We'll pick up with this next time.